Welcome to Metal Welding Lecture Series by Professor Joyjeet Ghose. This is the 9th lecture of the series. This lecture will be on resistance welding processes. He will be discussing about resistance welding principle, heat generated in resistance welding temperature profile, parameters in resistance welding, electrode in resistance welding, electrode degradation, effects of electrode degradation. He will also discuss the various types of resistance welding, like spot resistance welding, seam resistance welding, butt resistance welding, and projection resistance welding. The spot resistance welding cycle is discussed. Advantages, limitations, and applications of various types of resistance welding processes are also discussed, so do not miss and watch the full video. For the next video in the lecture series, please click the suggested video link above. You may also click on the playlist at end of the video to access all the videos. Please subscribe this channel and yes, do not forget to like and share. Also click on the bell icon to receive instant information of new videos uploaded.
Hello friends, welcome to this lecture 9 of a series of lecture on metal welding processes. In this lecture we will be discussing about the resistance welding. Resistance welding is a very important industrially accepted welding process, and it has wide application in industry, particularly in automobile industry. If you look at a car, if you go to the manufacturing unit in which a car is made, you will find that from 5,000 to 10,000 welds, spot welds are made, spot resistance welds are made in a car, normal automobile. So automobile industry is heavily dependent on resistance welding, or any sheet metal industries where you require to join two sheet metals. Resistance welding process is a very suitable process for joining such pieces. So what is resistance welding? It's basically a group of welding process, because there is a large number of resistance welding processes, 3 to 4 or rather 4 to 5 welding type of resistance welding processes. We will be discussing each one of them, and it produces coalitions of the metals with the heat obtained. Unlike other cases where we use an arc or a flame or a thermite mixture, here the heat is obtained from resistance of the work to electric current. Resistance to flow of electric current by the work in a circuit of which the work is a part, and the welding is completed by application of pressure. So essentially you will understand that here the heat is obtained by resistance to the flow of current by the two metal pieces at the junction, and the weld is completed by pressure. So it's essentially a plastic welding process. Here we do not melt the metal or bring it to a near melting temperature, and then we apply pressure to complete the weld. So basically here, okay, so before I go into discussing the working principle, a little bit of background. See, it was basically invented by this person, Elihu Thomson, in around 1977, and he invented a small low pressure resistance welding machine, and welding was accomplished by this machine by causing an internal resistance in the workpiece to generate the heat. So heat is generated by basically the resistance to the flow of current. And later on it was commercialized around 1880s. So nowadays industrially it's a very popular method for resistance welding. So here we use both the heat as well as pressure, so it's called a plastic welding process. So here we normally use or rather we use low voltage high amperage current which is passed through a very small area, so the current density is very high, and normally this current is passed through electrodes. The lower one is normally fixed electrode and upper one is movable electrodes. The upper one is clamped over the lower electrode, and in between the workpiece is placed. So the area here is very less, small area, contact area between the electrode and the workpiece is very small, and high amperage current is made to pass in the range of 1000 ampere, 2000 ampere, 3000 ampere, depending on the thickness of the workpiece. So that much high current is made to pass for a certain duration of time. So as the current is made to pass, because of the resistance to flow of current between the junction between the two metal pieces, which is placed in a butt welding condition in this, sorry, lap welding condition in this particular schematic diagram. So the fairing surface here, this is the fairing surface and this is the fairing surface. So the heat is generated in between the fairing surface, and because of this heat the temperature increases and temperature reaches almost to a melting temperature. Some material may melt, may not melt, and pressure completes the welding. So this is the basic principle of welding process. Now how it actually happens, we'll discuss in next few slides. How the temperature actually rises, how the heat is obtained. So basic equations of heat here will be H is equal to I square K I square RT, where I is the current in amperes, normally in kiloamperes, and R is resistance of the joint in ohms, and T is the time in seconds. And K is basically a constant because entire heat that is generated will not be used for the welding purpose. Some will be lost. So this constant K accounts for the heat loss. So this is the equation for the heat that is generated, and this heat is used or utilized for hitting the intersection between the two, or hitting the fairing surface to a temperature at which under pressure the welding can be completed. So resistance welding are basically of four types: butt welding, spot welding, seam welding, and projection welding. So this is a weld nugget that is formed under pressure between the two metal pieces, metal A, metal B, and high current is passed for a certain amount of time. A weld nugget is formed. So if you see the structure of the nugget, I'll show you in the actual picture. So here there will be columnar structure, and in the center there may be equiax structure. So okay, so let me discuss first these resistances involved. So there are 7 types of resistances involved. You may consider that these 7 resistances are in a series. So what are these resistances? 1 and 7 are electrical resistances of the electrode material. Now the electrode material that we will be using will be mostly copper alloy. So the electrical resistance will be very less. So the heat generated will be fairly less in the electrode, and this electrode is water cooled. Very important, this electrode is water cooled. So if you see the temperature profile here and the resistance profile here, at 1 the resistance is less and the heat is also, temperature is also less. At the junction, that is at 2, between the electrode and the one of the base metal, or the 2 and 6, I am talking about 2 and 6, at the junction between the electrode and the base metal. So here there is a highly conducting, high thermal conducting electrode and the base metal here at the interface. So here the resistance will be high. However, because the heat is dissipated rapidly because of the high thermal conductivity of the copper electrode, and this copper electrode is water cooled, because of these two reasons the heat that is produced is somewhat dissipated, and we can lower the temperature of these two junction, and therefore the chances of welding is reduced of the electrode, welding of the electrode to the workpiece material is reduced. This is very important. This is very important. The junction 2 and 6. 2 and 6 is the interface. This is 2 and this is 6. It is the interface between the electrode and the base material. Now here we reduce the temperature. How do we reduce the temperature? By using an electrode material which is having high thermal conductivity. Whatever heat will be is produced will be dissipated rapidly by the electrode, and secondly we reduce the temperature here by making it water cooled, and making it water cooled, the life of the electrode is also prolonged. So therefore the chances of the electrode being welded to the base metal is reduced significantly, and you can see here the temperature is less. And then comes the resistance of the base material, that is 3 and 5. These are the base materials. The resistance will vary if they are of different material. If they are same material, the resistance will same. In this case, resistance being same, so that it is symmetrical. here. Because the resistance is decreasing, you can see the resistance is decreasing, the temperature also will decrease. So this is the peak here and the temperature will decrease here. Now suddenly at this point, at the junction, that is 4 is very important for us. We want the temperature to be maximum at the 4, and it is actually the temperature is maximum at the 4. Therefore the welding nugget actually takes place at the junction 4 because the gap, the interface or the faying surface having high resistance to flow of the electric current, and therefore H is equal to I square RT. By that formula, heat will be generated, and which will be maximum at the junction 4. So heat will be maximum here, and under the pressure the weld will be completed and you form a weld nugget. So this is basically a spot welding profile here. This is a particular type of resistance welding. Of course, this is variation, but you can understand the basic principles by the spot welding example. Okay, so you can see here sometimes the nugget is not fully formed, so it will not have sufficient strength. Okay, so this type of spot weld is not wanted, and you can see this is a perfect spot welding. You can see the columnar structure, and sometimes in between center you have equiax structure, but here in this particular example it is mostly columnar structure, and this is a phenomena called expansion, expulsion. We do not want expulsion in spot welding, so that is very important. So our objective is to reach this type of or obtain this type of welding nugget. Okay, parameters that influences the resistance welding. First of all, the welding current, very important. The higher the current, larger will be the size of the nugget. However, if you keep on increasing current, after a certain point of time, it will result in an expulsion and electrode deterioration, and sometimes the electrode may even stick to the workpiece. So a balance has to be maintained. By and large, you can say if you keep on increasing the nugget, the current, the nugget size will increase, but up to certain level, then it will create problem. Welding time. Now, if the current is low and your welding time is more, then it will not make a good weld. And when the welding current is sufficient, if you keep on increasing the time, if the time is more, slowly the weld nugget will increase, and it will obtain a size of the area under the electrode. And that is good. At that point, that it should be stopped. Otherwise, if you keep on prolonging this, then expulsion again may takes place. So that also don't want. So you have to restrict the welding time. Welding force is also very important. Welding force is important from 2 points of view. One is the contact resistance, and other is the contact area. Now, of course, the welding force is increased. The contact area also increases because the asperities will fall out, and the contact area will increase. And of course, if you apply more pressure, the contact resistance will decrease. However, we do not want, having said that, this obviously will decrease the heat generation, and however, we do not want too low welding force. That will not give us a very good welding. So a balance has to be maintained between a low welding force and a high welding force. And high welding force, of course, will decrease the life of the electrode. Contact resistance is also very important parameter. When the temperature increases, some of the surface contaminants will burn off in the first couple of cycles, and the metal will also be softened at high temperature. So the contact resistance generally decreases with increasing temperature. So when the temperature increases, the contact resistance decreases. Okay, the material properties are very important. So if certain material which you are joining has high thermal conductivity and low resistivity, then that creates a problem. Materials like silver, copper is difficult to weld by this process. These are ideally a very good electrode material, but these are difficult to weld by resistance welding method because it quickly dissipates the heat, and the resistance is also low, so the heat generated will also be low. Surface coating. Surface coating is a very tricky situation in resistance welding process. So it may create a huge problem. So accordingly, you have to modify your process parameters to be able to weld in if the material you are joining has surface coatings. The coating may be removed or squeezed out by the pressure of the welding. Geometry is very important. Ideally, you want the electrode to be electrode face to be as small as possible, but it should have sufficient mechanical strength in order to localize the current to give the better weld. However, you are restricted to the amount of pressure and the mechanical property of the copper alloy you are using and the thickness of the metal sheets. So these are the parameters which affects the resistance welding processes. So what are the electrodes that are used? We use normally copper electrodes, which is covered by ISO 5182. There are two types, class 2, class 3, which are most commonly used. Class 2 consists of the copper alloyed with chromium or chromium zirconium, and class 3 is alloyed with nickel and silicon. Class 2 is normally used for low carbon and high strength steel, and for harder materials like stainless steel, we use the class 3, that is the copper alloyed with nickel and silicon. Okay, electrode will degrade and you require dressing, or sometimes may have to change the electrode. You can see the tip here. Under pressure of repeatedly using it, this diameter keeps on increasing. So here it is small diameter, and you can see the diameter here. The diameter will increase, but it can undergo geometrical degradation. It may undergo metallurgical degradation also. So a electrode in resistance welding has a fixed life. There is number of welding that it can do. After a certain point of time, one has to replace it or dress it. You can see with the number of weld which is being done, the nugget size is decreasing and the tip diameter is increasing. So the size keeps on decreasing with increase in the nugget diameter. Increasing in the electrode diameter. So what are the advantages of resistance welding? It's efficient for mass production. It is very fast. Nothing is consumed. Skill of the operator is required is very less. Sometimes it is possible to weld dissimilar metal also. But equipment is costly, and certain resistance welding processes are limited to lab joints only. So this is a spot welding process. Spot welding already we have discussed. Basically, first we apply pressure. This is the weld nugget that is formed. Let me show. This is a spot welding machine, manual spot welding machine. Robotic spot welding machines are also available. CNC controlled spot welding machines are also available. So here basically the electrode can be modified to suit the requirement. Okay, I was looking for this figure. So this figure systematically explains the process of spot welding. So here this is a fixed electrode and this is a movable electrode, and in between the fixed and the movable electrodes in lap joint configuration, the two metal pieces are placed. Electrode is brought down at this point and then we apply pressure. So pressure is applied, you can see the force here. The force increases, and then at a constant force we maintain a constant force here. So up to this point, up to 4, end of 4, we maintain a constant. From 2 to 4, we maintain a constant pressure. Under constant pressure, for a certain specific period of time, we apply electric current. Now, not just electric current, it's a high density electric current. High density electric current because the current is passed through a very small area and the magnitude or the amperage is very, very high. So high density electric current is made to pass. As a result of the resistance to flow of current in between the junction in the fairing surface, the heat generated will be very, very high, and it may even reach a melting point temperature. It may melt a certain amount of material also. Under pressure, the weld nugget will be formed, weld nugget will be solidified, and after a certain period of time, which is predetermined, which is design time, will relieve the load here slowly, and then we pull off the upper electrode. So this takes how much time? Very less time, maybe less than second or 1 or 2 seconds. So depending on thickness, of course. So this is a very, very fast process, and sometimes you use another cycle of current just to relieve the stress that is developed, thermal stress that is developed in the spot weld. So this is the spot welding method, a very efficient technique to weld thin sheets at different locations. Then we have butt resistance welding. It's basically similar to that of spot welding. Only difference is that here two metal pieces are brought in end to end, and electric current is made to pass. This is the electrode. So resistance will be very, very high, and under pressure the welding will be completed. A similar process is called flash butt welding, where we don't switch on the current. We switch on the current when it is a certain distance from the this fixed workpiece, one movable workpiece and the fixed workpiece, and because it is a certain distance, the current is switched on, arcing will take place, and the temperature will increase because of the arcing, and finally it is pressed onto this fixed workpiece, and the welding will be completed. So this is flash butt welding, and you get this kind of certain bulging may occur under the pressure, which can be turned. Okay, then we have seam welding. Seam welding is a efficient method of joining obtaining continuous overlapping joint, and mainly used for making tanks, ignition tubes, etc. So here the copper electrodes are replaced by electrode wheels, which copper wheels. Now the copper wheel is rotating over the two metal pieces which are joining, and the current is switched on, and if you can control the settings speed, we can obtain a continuous joint or a nuggets formed at different location, depending on how we are controlling the current. So you can obtain a continuous seam type of welding, and that's why it's called seam resistance welding, but the process of heating remains same. So this seam is basically a overlapping nugget. This is spaced nugget. Okay, so last one is projection welding. It's very interesting here. First, what you do, in one of these sheets you make a projection here, and once you make a projection and brought in contact with the workpiece, and then you pass the current, electrical current, and because of the current this will collapse and form a joint. So this type of again, because of the resistance heating, this type of joining of metal pieces are called projection resistance welding. You can see here, this is a projection resistance welding. So these are the four resistance welding processes that I have discussed: spot welding process, butt welding process. Butt welding can be of two types: upset butt welding and flash butt welding, and you have seam welding and projection welding. So these are the four major resistance welding processes. So thank you for watching this video. We come to the end of it. I hope you have liked this lecture, and in the next lecture we will be discussing about electron beam welding. Thank you.